Let's do exercise 4 here. Find all complex zeros of f of x equals x cubed minus x squared plus 4x minus 4. So this is the first time we're seeing that complex numbers being referred to in our exercises. We had a little introduction in the previous video. And just be aware that this includes real zeros. So everything we've done up to now applies as far as our remainder theorem, factor theorem, rational root theorem, all that applies. And there just might be a little bit more going on, and we'll see what happens as we start investigating this. So we start out in our usual way. We want to try to find zeros, and a good way to start is to use the rational zero theorem. So I'm going to look at fractions of the form p over q, where I look at factors of the constant coefficient over factors of the lead coefficient. And make sure you get those in the right place. And the way I remember this is, if the lead coefficient is 1, all the zeros there won't be fractional zeros. They'll just be integer valued zeros. So it's those factors of the constant coefficient that give me the integer values, and that's why they go up in the numerator. Maybe that's a rather complicated way of remembering that, but that's what I do. So factors the constant coefficient. Constant coefficient is -4. So we have plus or minus 1, plus or minus 2, plus or minus 4. And we're going to divide by factors of the lead coefficient. Lead coefficient here is just 1. So we only have to look at plus or minus 1, plus or minus 2, plus or minus 4. So there actually are only 6 possible rational number zeros. Now, not all zeros are rational numbers. There are real numbers that are not rational, like square root of 2. We've seen that could be a 0. It's a real 0 that's not rational. And there are also complex number zeros that are not real, and we'll see that in a little bit. So let's start looking for zeros. Let's try 1. And so I'm going to do my synthetic division. Take the coefficients 1, -1, 4, -4 from the original polynomial. And so I bring down this 1. 1 times 1 is 1. Add these, I get 0. 0 times 1 is 0. Add these, I get 4. 4 times 1 is 4. Add these, I get 0. So here f of 1 is 0. And so that, that means x minus 1 is a factor. So I lucked out here. I had good luck right on my first try. And so what can we say? We can take our function f of x, which was x cubed minus x squared plus 4x minus 4. And we know it factors into x minus 1 times the quotient that we got when we divided. So we have to read that off from our synthetic division. 4 is constant, 0 is x to the first, 1 is x squared. So this is x squared plus 0x plus 4, which is x squared plus 4. And now, since we have a quadratic, we can just try to solve the quadratic, right? We can just try setting x squared plus 4 equal to 0 to find remaining zeros. But here we get x squared is -4, and x squared is, there's no real solutions, right? Now we can write x is equal to plus or minus the square root of negative 4. And here's where I'm going to bring in complex numbers. This can be thought of as plus or minus the square root of 4i, or plus or minus 2i. So notice if I square 2i, I get 4i squared, which is 4 times negative 1, or negative 4. So 2i is a square root of negative 4. If I square negative 2i, I get negative 2 squared I squared, which is, maybe I'll write underneath here, positive 4 times negative 1, which is negative 4 also. That's the other square root. So this is just meant to convince us that, sure enough, 2i and negative 2i are solutions to that equation, x squared equals negative 4. And now let's see. We wanted to find all complex zeros. So we got the complex zeros are, well, we found the number 1, we got 2i, and we got negative 2i. So just notice there is just one real zero. Two of those zeros are imaginary numbers. And that's the answer to the question. But again, I'm going to say a little bit more on the end of this video about what's going on with this polynomial. Let's go to another sheet. I can take my function f of x, which was x cubed minus x squared plus 4x minus 4. Now we saw that we could factor it as x minus 1 times x squared plus 4. And yet, if we apply the factor theorem to these complex zeros that we found, x minus a 0 should be a factor. So we should be able to write x minus 2i as a factor. The other 0, minus 2i, x minus a negative 2i would give me x plus 2i. And it's true that we can factor using complex numbers now. We can factor that polynomial into 3 linear factors. Just note, if this seems surprising, that we can check by multiplying out x minus 2i times x plus 2i. We get x squared plus 2ix minus 2ix, and then we're going to get minus 4i squared. Those terms cancel out, and that minus 4i squared, that's actually a negative 4 times a negative 1, because I squared is negative 1. Negative 4 times negative 1 is plus 4. There's that x squared plus 4 factor. Just a comment about the graph of f of x equals x cubed minus x squared plus 4x minus 4. Only real zeros, real number zeros, appear as x-intercepts. So we've talked a lot about how zeros are like x-intercepts, but here we would say there are 3 complex zeros, but this function f has only one x-intercept, even though there are 3 complex zeros. The y-intercept, by the way, for this graph is -4, right? That's easy to see from the statement if we plug in 0 for x. And now, I checked on Desmos ahead of time. This graph just has a little bit of a wiggle to it. I put a little too much wiggle into it. It is a 3rd degree cubic graph, but it's just got a little sway to it. So it's kind of the boringest kind of graph you can imagine. So notice there's just one x-intercept, but there are 3 complex zeros. One, what were the other two? 2i, and -2i. Again, the thing is those complex zeros, they're there, but they don't have anything they don't appear on the graph in any way. And that's it. And we will talk more about complex numbers in the coming video.